In our last lesson that you watched on EduCanon, you learned about the difference between ionic bonds and covalent bonds, and you also learned about the octet rule. So today we're going to talk more specifically about ionic compounds and how they're formed, how you can predict how they're going to form, and a little about metallic bonds as well. So now just a little bit of a review from what you saw in your video yesterday. Ionic compounds are when we get a transfer of an electron or more than one electron from a metal to a nonmetal, and the result is that you get a cation in the case of the metal and an anion in the case of the nonmetal. And so an ionic bond is actually just based on Coulombic attraction between a positively charged and a negatively charged ion. And it's important to remember that when an ionic bond forms, the ions that you get do not have the same properties as the elements that they came from. So for example, we learned that sodium metal reacts violently when you put it in water. And chlorine, in its elemental form, is a green gas that's poisonous. But you take both of them and you transfer some electrons and then form an ionic bond, you get a white crystalline solid that we frequently put on our food. And so it is neither poisonous nor highly reactive in water. So the resulting compound that you get when you make an ionic bond or an ionic compound does not have the same properties as the things that you start with in their elemental form. So now let's practice writing some of the formulas for these ionic compounds. So a formula is a shorthand way of us telling how many of each kind of ion is in particular type of ionic compound. And so we use little subscripts in order to show that. And it is important that for ionic formulas, because they form large crystalline structures, we just show the lowest whole number ratio. So a given crystal of salt will have billions of sodium ions and billions of chloride ions. But what we care about is that the ratio is 1 to 1. That NaCl implies that there's one sodium ion for every chloride ion that's present. And so in order to write an ionic formula, we need to know the charges of both of the ions that we're starting with. So if we form an ionic compound from potassium and oxygen, for example, if we look at our periodic table, potassium is an alkali metal, and so that means it's going to have a +1 charge, and oxygen is found in the 6th column, so it wants to gain 2 electrons to have a full octet. Okay, so we have K plus and O2 minus. So if we put both of those together, we would have, if we just use one of each, we would have a negative charge left over. All right, so in order to satisfy that -2 for the oxygen, we need 2 potassiums to balance out that charge. So our formula for potassium and oxygen is K2O. So that tells us that we need 2 potassiums, which both have a +1 charge, and 1 oxygen, or 1 oxide ion, in order to get a neutral salt crystal. Now we can do the same thing for magnesium and nitrogen. So magnesium is going to form an Mg2+ ion. It's in the 2nd column. And nitrogen is in the 5th column. It's going to form N3-. So in order to get a neutral charge with these, magnesium has a +2 and nitrogen has a -3. We sort of need the lowest common multiple, if you remember that from math. So if we have 2 magnesiums, then we now have +4 with the nitrogen with a -3. So that's not going to work. So we need another nitrogen, so that gives us a -6 for the nitrogen side, and we would need 1 more magnesium to satisfy that. So that gives us a formula of Mg3N2. So we can go through these last two a little bit more quickly. So barium is in the 2nd column. It will have a +2, and sulfur has a -2. So a +2 and a -2 balance each other out fine. So our formula for that one is just BAS. And then last but not least, we have sodium, which has a +1. Fluorine has a -1. And so our formula for that is just going to be NaF. So now we just found the ratio of different ions that we need in a given ionic compound in order to have it be neutral to balance out the positive and negative charges. But it's important to remember that in ionic compounds you have a whole array of ions, and all we figure out is the ratio. So for every sodium ion there is one chloride ion, and that ratio represents how many there are in an entire crystal. And we call this an ionic crystal. It's an ordered array of ions, and as you can see here in the diagram, it's very tightly packed, and there are several different ways that a crystal can be ordered that are based on both the size of the two ions and also the ratio of the two ions. I'm not going to make you learn the different crystal arrays or anything like that, but just be aware that when you see a formula for something like sodium chloride, which is one sodium and one chlorine, you don't just have one of each of those ions in isolation. They're actually present in a large array, or an ionic crystal, which is what gives us those little white crystals that we sprinkle on our food. So now moving on to something a little bit different, let's talk about metallic bonds. And so metallic bonds are similar to ionic bonds because there's an attraction between two different charges. But in a metallic bond, we have positively charged metal ions that are held together by a sea of electrons that move through them. And so this happens because, as we learned, metal ions have usually just a couple of extra valence electrons that they want to get rid of, and they don't hold on to them very tightly. Remember, metals tend to have lower ionization energies than nonmetals. And so what you end up with is these positive ions that are packed together in a metal, and the electrons move pretty freely from one nucleus to the next, and that is what gives metals their properties. That's what causes them to conduct electricity very well. So electricity is just the movement of electrons, and it's also the reason they conduct heat very well. Metals can be present in their pure form, or we also find them as alloys. And an alloy is a metal that has other metals added to it. So gold is one example. So 24 karat gold is pure gold. Anything lower than that has something else added in. And that's how we get these various colors of gold that you can find in a jewelry store. So gold itself has a yellow color, so that's what color 24 karat gold would be. But then sometimes other elements are added and you can get a rose gold or a white gold. And different metals come together to change the properties of the metal. So it could make it stronger, or it could make it more durable or more malleable, or things like that. The other way we find metals is as ores, and these are natural rocks basically that have different metal ions or metals present within them. So ores are geological deposits that contain relatively high concentrations of metal-containing compounds. Okay, so that sums up both ionic and metallic bonds, and next time we'll talk a little bit more about covalent bonds.